Welcome to Homework Lib.
So in this question, we have an atom that is lithium hydrogen. And we want to know what is the amount of energy required for this atom to go from energy level 3 to energy level 4, and what is the wavelength of the photons that will be emitted during this process. So in question 1, we ask what is the energy change when it goes one energy level up. So in order to do that, we know that the amount of energy in each energy level is given by L times L plus 1 h bar squared over 2I. So following this equation, we will be able to find the energy at energy level 3 and the energy at energy level 4. And then if we subtract them, that will give us the difference of energy required in this process. Okay, so if we want to use this equation, the first thing we need to do is we need to find out what is I. And I is a moment of inertia. Moment of inertia is given by the equivalent mass times, or the relative mass, times r squared. And in order to find the mass, the relative mass, or the reduced mass in this two-body system is given by reduced mass equals m1, m2 over m1 plus m2. So here, m1 and m2 are the mass of lithium and the mass of hydrogen, and we are given that the mass of hydrogen is 1.67 times 10 to the negative 27 kilogram, and the mass of lithium is 1.17 times 10 to the negative 26. Okay, so together this gives us 1.46 times 10 to the negative 27 kilogram. So this is a reduced mass, and we can see that it's still pretty much dominated by hydrogen, because lithium is so much heavier than hydrogen. So really, in this case, hydrogen is the one that's rotating around the lithium, not the other way around. So once we have the reduced mass, we can go to the next step when we find the moment of inertia. So the moment of inertia is mr squared. R squared is just r is the distance between lithium and hydrogen, which we have found, which we were given in the question. So r is 0.159 times 10 to the negative 9 meter squared. So this gives us 3.7 times 10 to the negative 49 kilogram meter squared. Okay, so once we have the moment of inertia, we can now use this equation. What we're looking for here is a change of energy from L equals 3 to L equals 4. So for L equals 4, L times L plus 1 is 4 times 5. And then for L equals 3, this part is 3 times 4, and all the other parts are equal. It's h bar over 2I. So if we calculate this, we find that this is equal to 4 times h bar squared over 2I. H bar squared is 1.055 times 10 to the negative 34 joules per second. The whole thing squared. And 2 times moment of inertia we found in the previous equation, 10 to the negative 49 kilogram meters squared. This turns out to be 1.20 times 10 to the negative 21 joule. Or if we want to use electrovolts, which is a more convenient unit in this case, is 7.5 times 10 to the negative 3 electrovolts. So that is for part A. For part B, we want to find the wavelength of the photon emitted in this case. So we already know the amount of energy changed is 7.5 times 10 to the negative 3 electrovolts. And for a photon, the amount of energy carried by a photon is related to its wavelength by energy equals hc over lambda, where lambda is the wavelength. And we have to note that previously we have h bar. In this equation, we have h, not h bar. So they differ by 2 pi. So we can use this equation to find the amount of wavelength corresponding to this much energy by just rearranging it. So H, I will use electrovolts in this case because I think it's a more convenient unit, and also because I know what the energy is in terms of electrovolts. And then it's 3 times 3 times 10 to the 8th meter per second is the speed of light. And then the change of energy is 7.5 times 10 to the negative 3 electrovolts. So if we calculate it, we will get 1.66 times 10 to the negative 6 meter, or I will write it in micrometer, which is 166 micrometer. So this, it's not in the visible range, we will not be able to see this photon.